let me just grab one thing before we do that. Oh, you started the recording already. Okay, great. Today we have a really exciting speaker, Elizabeth Kelley. She's my, I don't know, not academic sibling for real, but she also goes to the University of Minnesota. She's on the job market this fall. Today, she's going to talk to us about scattering diagrams and a theta basis for generalized cluster algebras, but with reciprocal coefficients. But before she does that, I want to remind us a little bit about the community guidelines for the Graduate Online Combinatorics Colloquium. The first one is that we're all learning. So Elizabeth's learning, I'm learning, you're learning. The second one is everyone has something to contribute. So you have something to contribute, you have good questions. Elizabeth has something to contribute and she has good questions as well.
Hopefully I have something to contribute.
And finally, no one has all the answers. So I don't have all the answers. You don't have all the answers. Hopefully Elizabeth has a few of the answers, but if she can't answer them, then maybe we'll try and figure them out together. So without any more preamble, Elizabeth, take it away.
Thanks, Galen. So thanks to the organizers for putting together the online colloquium and for giving me the opportunity to give this talk. So I want to talk a little bit about a project that I have been working on for the last year or so. This is a project about cluster algebras, of course, because everything I do is about cluster algebras, but also using scattering diagrams, which are this construction from algebraic geometry that I did not understand at all a year ago and hopefully understand a little bit more about now. This is joint work with Mandy and Greg. And so let me maybe start by giving you a little bit of a roadmap for the structure of my talk. So I think of this talk as having sort of two parts. The first half is more expository. So that's the left side of this diagram. I'm going to talk a little bit about what a cluster algebra is in case you're not familiar. I'm going to talk a little bit about what this scattering diagram construction is. I'll define a couple things called path-ordered products, broken lines, mutation invariance, just some properties and objects that we'll need. And then I'll talk about what the theta basis is, how it was defined for ordinary cluster algebras, and why we wanted to define it in the first place. And then the second half is more about the project that I have actually been working on. So I'm going to define a generalized cluster algebra, which is this object that I've been studying and making people listen to me ramble about for quite a while now. And then I'm going to fill in this sort of dotted parallel to the first narrative. So I'm going to go through and explain how we can modify the construction of a scattering diagram so that we can work instead with these generalized cluster algebras. I'll define a lot of these same objects in the generalized setting. And then I'll conclude by saying something about how this lets us define the theta basis for these algebras also. And I guess maybe before I start with the scary slides, I will say that a lot of these slides have what look like sort of intense or large technical definitions on them. So in some sense, I think I'm legally obligated to show you these technical definitions so that you can't walk away and say, well, Elizabeth never actually wrote down a definition of a cluster algebra, what the heck? But you don't need to feel like you need to carefully read or absorb all of these definitions to follow the talk. I'll try to, as we go, highlight what you actually need to take away from each slide. So in some sense, you could just look at the diagrams, look at the highlighted keywords, and listen to what I say and not really miss the substance of the talk. So don't be intimidated by the length of some of the definitions. So with that said, let me give you my elevator pitch for what a cluster algebra is. So cluster algebras were defined by Fomin and Zelvinsky in 2001. It's a type of commutative algebra where we have a little bit of extra structure. So the generators of the algebra, which we call cluster variables, appear in standard fixed size subsets called clusters. And the nice thing about these generators is that instead of needing all the generators to generate the algebra, you can take one cluster and use what are called standard exchange relations to generate the rest of the algebra. So these exchange relations tell you how to write the remaining cluster variables or generators in terms of the ones you started with. And then you can sort of turn this crank and generate the rest of the algebra. So in some sense, it's even better than having an algebra where I can write down generators and relations, because I can tell you even less information about the algebra and still get everything. And so if I wanted to communicate to you what cluster algebra I was thinking about, what I would do is I would tell you what's called about what's called a seed. And a seed contains three things. So it contains first this list of x variables, x1 through xn, which is called the initial cluster, and that's a set of cluster variables. And then it contains what's called a coefficient cluster. These are the y variables. And this coefficient cluster is the same size as the cluster. And then it also contains an exchange matrix, which has integer entries and is skew symmetrizable. And this matrix is what tells you how to write down the exchange relations. So all the information about those relations is encoded in this matrix. And in some cases, this matrix is actually maybe an adjacency matrix for a quiver, and there are some nice models, but I'm not going to talk at all about this entirely different and really beautiful branch of cluster algebra theory. And then more equations. So in a cluster algebra, I said that the cluster variables appear in what are called clusters. And so one question that you might ask is, is my choice of initial cluster special? How do I get to the other clusters? And so we define this operation called mutation, which takes us from one cluster to another. And so essentially, you should think that mutation takes one cluster variable and it swaps it out for some unique other cluster variable. So it's an involution, and it's completely well-defined. Like if you apply mutation in one direction to a seed, there's a certain other seed that you always get. And you can completely explore the cluster algebra by iteratively mutating in lots of different directions. And how many mutations that takes depends on the type of cluster algebra and all sorts of fun combinatorial questions like that you could ask yourself. And so the only important thing I think that you need to take away from this slide is that when you look at the relations that I wrote down, for example, if you look at, that doesn't highlight very well, but so if you look at the equation for xi prime, we use the primes to denote the new variables that we're swapping in. If you look at the bottom relation, you can see that it's a binomial. And so one really hallmark feature of cluster algebras is that all of these exchange relations are binomials. And this is sort of the important structural thing that I want you to remember for the second half of the talk. So if you take nothing else from the slide, things are binomials. Okay, and you can kind of ignore the bits that I grayed out. So these look complicated, but in most cases, we work in a certain coefficient field, and these turn out to just be factors of one. So we can make these equations a little bit more manageable.
Do you mind taking a second, sorry, to explain exactly what you mean by binomial in this case? Like in what variable and what are the coefficients exactly?
Yeah, so actually, let me rudely go to the next slide. I'm about to do an example, and I think that I can show you better there.
Cool, thanks.
Yeah, that's a really good question, though. Thank you. So the example that I want to show you is if you know the Dinkin diagram classification for finite type cluster algebras, it's type A2. If you don't, that's fine. Those are just words. So here we're going to start with a seed where we have two variables, x1 and x2. We've got two coefficients, y1 and y2. And then our exchange matrix is just 0, 1, minus 1, 0. And let's suppose that I wanted to mutate in direction 1. So what I did is I applied all the equations from the previous page. And I think what I want you to look at, Alex, is here. This is really the one that you want to look at when you're thinking about binomials. So each term in the numerator, these terms could look like a product of yi's and xi's. There's not an a priori limit on, like, there's nothing saying I couldn't have something in a larger cluster algebra that had lots and lots of factors in that monomial, right? But it's always the exchange relation itself. So let me clear this because I don't want to say something a little deceptive. So if we look on the previous slide, this is coming from the fact that we've got this one product and then a second product. Now, the one tricky thing is that as I continue iterating mutation, it may be that one of these xj's, if I write it in terms of previous variables, it itself might have multiple terms. So I can end up with variables where I have more than 2 terms in the numerator. So when I talk about it being binomial, what I mean is that the exchange relation has this binomial structure. I don't mean that every cluster variable can be written as a binomial over a monomial. So in some ways, that's a little bit of a subtle point. So I'm glad that you asked, because I think what I said initially might have been a little deceptive. Does that answer the question?
Yeah, thanks.
Great.
Makes sense. It's like the two thin. I think I was getting a little bit distracted by the denominator also, but once you grade that out.
So the denominator, I think, is a little distracting because as people and mathematicians, we often like looking at polynomials, right? And this isn't quite a legit polynomial. It's a Laurent polynomial. So you will always be able to write it so that the denominator is just a monomial. So then we often will, if you want to write it out as something that looks like more of an honest to God polynomial, you'll just write the negative powers of the denominator. And this is actually an interesting structural property of cluster algebras, that any cluster variable can be written as a Laurent polynomial in terms of any cluster. It's something called the Laurent phenomenon, and it's one of the things that makes cluster algebras so interesting to study. So you accidentally stumbled onto one of the really big ideas of cluster algebras. Right, so in this example, I'm just showing, if I mutated in direction 1, here's how the seed would change. There's not a lot else that I want to say about this example. And so if I continued alternating the direction of mutation, I would eventually get this set of 5 cluster variables, and I'm going to claim these are the only cluster variables. To get back to the initial seed, I would actually have to mutate more than just these 5 times, because if I'm tracking the coefficients, there's some swapping that goes on, and I don't get quite back to the original seed after just seeing each of the unique cluster variables. But this is sort of an aside. There's like maybe some interesting enumerative questions you could ask, but unfortunately it's a tangent for what I'm trying to talk about. And so as Alex has already discovered, there are some interesting and wonderful structural properties of cluster algebras. So one of these is the Laurent phenomenon that I mentioned. The other is what's called positivity. And all that means is that when I write out the terms in these Laurent polynomials, it turns out their coefficients are always positive integers. And it's not just in little nice examples, it's even in really big examples where we start having infinite numbers of cluster variables. And so as combinatorialists, this should be really, really exciting to us. And I guess not everyone here maybe identifies as a combinatorialist, but hopefully you have at least some interest in combinatorics. And so the reason it's exciting to us, right, is because when we see positive integers, we see things that we might be able to count. So there's a whole story that you can tell here about about combinatorial objects called snake graphs that you can use to come up with these coefficients. And I would love to tell this story, but unfortunately it's also a tangent. But so one natural question that comes out of these structural properties, though, is, are there good bases that I can write down for cluster algebras? And by good, in some sense, I'm not really going to define what I mean, but I want to say that these good bases have properties that are kind of inspired by the Laurent phenomenon and positivity. So one that I'll call out is I would really like if I multiply two elements of my basis, and then I write that product out in terms of, things from the basis. I would love for all those coefficients to be positive integers, right? I would like to have these positive structural constants. And I'm not going to talk a lot about any of these properties. I just want to give you a sense of what we might be looking for in a basis and why people are really interested in finding these bases. So that's my motivational pitch for why we would want to define something like the theta basis that I'll eventually get to. So people were sort of on the hunt for these good bases. Okay, so switching gears a tiny bit. Everything that I've talked about has been from a very algebraic perspective. So from a geometric perspective, you can also study cluster algebras by studying what are called cluster varieties. Cluster varieties appear in these pairs called cluster ensembles. And these were defined by Fock and Gontarov. And unfortunately, I don't remember the year they did this off the top of my head. And so if you remember, when I talked about the seeds for cluster algebras, we had these clusters of cluster variables and these coefficient clusters. So here, what we call the A variety or the cluster variety is going to encode information about the cluster variables or the xi. And the X variety, confusingly I know, is going to encode information about the coefficients or the yi variables. And this naming convention is kind of tragic, but it is what it is. You just have to remember that the X variety does not actually tell you about the X variables. Okay, and so one comment that I'll make for people who are familiar with some of these words, so mostly I think this comment is for Esther and Libby, possibly others. So there's a special case of cluster algebra where we have something that we call principal coefficients. And in this case, we can define the cluster variety with principal coefficients, which just sort of marries these varieties together in a particular way. So for the rest of the talk, I'm basically going to ignore the X variety. All of my examples are just going to be for the A variety because for two reasons. So one, it'll be a little simpler so we can actually get some purchase and see what's going on. Two, it means that things will stay in 2 dimensions and then I can actually draw things. So for the sake of prettier diagrams and a simpler narrative, we're basically going to forget that these coefficients exist. Okay, so now we're ready to set up the idea of a scattering diagram. So scattering diagrams are tools from algebraic geometry that can be used to study some of these structural properties of cluster algebras. So sort of most famously, I guess from my perspective, Gross, Hacking, Kiel, and Konstevich use scattering diagrams and the theta basis, which we have not defined, to prove the positivity phenomenon for ordinary cluster algebras. And one thing that I want to point out is that their paper doing this came out in 2018, and ordinary cluster algebras were defined in 2001, and the positivity conjecture was made in that original paper. So positivity is actually a pretty hard property to get at. In the intervening years, there were many proofs in like special cases. So for instance, the combinatorial object I mentioned earlier, a snake graph that was used to prove positivity for some classes of cluster algebras, but it took this long for there to be a general proof. So when I call scattering diagrams powerful, to me, they are very powerful tools. And I find it sort of beautiful that they were able to answer this very hard question. So here's an example of a scattering diagram. And I think Galen will find these kind of exciting because she can think about collections of cones. So a scattering diagram is basically a collection of what we call walls and automorphisms that are attached to those walls. So a wall is a codimension 1 cone, if I want to be very technical and precise. Since we're going to live in dimension 2, or I guess I wrote rank 2 here, and what rank 2 means is it means that there are 2 variables in each cluster, so everything is living in 2 dimensions right now. So here we're just going to think that our walls are lines. They could be a full line or they could be a ray beginning at the origin. And the automorphisms are going to be written as formal power series in a variable z. You should think that z is just sort of encoding the cluster variables. So for example, here where I have the function 1 plus z to the minus 1, 0, that's really like, I could have instead written 1 plus 1 over x1, but it's easier and more consistent with the notation from algebraic geometry to write it the way that I've written it on the diagram. I guess I started out when I was learning about scattering diagrams, always writing things in terms of the cluster variables. And then my collaborators broke me of that habit very, very quickly by pointing out that I was writing things that were very confusing to them. So I'm sold on this notation now. Okay. And so big scary definition. So just like a cluster algebra is defined by a seed, we can talk about the data that's used to define a scattering diagram. So loosely, what we want to think is that we've got some lattice, n, that's got some bilinear form defined on it. And then there's a dual lattice, m, and both lattices, n and m, have sublattices. And our diagram is going to live in the sublattice of m. And you really don't need to dig into this lattice structure for the talk. It's actually kind of takes a little bit of time to absorb. What I'll say for people who maybe have a little bit of familiarity with cluster algebras is that the sublattice structure is going to say something about the type of cluster algebra you're working with. So the sublattice that the scattering diagram lives on will be different for, say, type A2 versus type B2 versus type C2, etc. And then we also, part of the information in this sublattice is in cluster algebras, I have just told you there are cluster variables, but we can also think about freezing some cluster variables, and this sublattice maybe tells you something about directions you can mutate in. But so for our purposes, just remember that there are 2 lattices. There's some set of integers that we use to define the sublattices, and we've got some bilinear form. Okay, and then we also have something called a seed for a scattering diagram. And here, a seed means a choice of basis for these lattices. So what you do is you choose a basis for the first lattice, n, and then because the other lattice is a dual lattice, this defines a basis for that lattice. And then you do some scaling using our collection of integers to get bases for the sublattices. We can also define something called an initial scattering diagram, which basically, when we draw a scattering diagram, you start by drawing certain walls, and then there's some algorithms that let you fill in the rest. So the initial scattering diagram is just sort of a definition that tells you here are the initial walls to draw based on the data that I gave you. And then you can turn the crank and fill in the rest of the walls. And that's really as much as you need to understand about these definitions.
Can I ask you, maybe this will be answered in the example, but why is it called a scattering diagram?
Okay, so I won't answer that right away in this example. It'll come up a little later. But basically, let me give you a slight preview, because I also don't know how much of the material in this talk we will end up getting through, just because in an audience that's not as familiar with cluster algebras, I don't want to rush us through and then have it be incomprehensible. So the reason it's called a scattering diagram is because later we'll want to think about certain sets of paths that will make up what are called broken lines. And these are basically linear paths that approach on a certain slope. And when they reach a wall, based on the terms in the wall, they can scatter at different angles. So just like maybe like light bending or refracting, you can get things like it bounces off or it goes through but at a slightly changed angle. And this depends on the slope when you're coming in and the function on the wall. So in some sense, there's like literal scattering going on.
Thank you.
Yeah, no, it's a good question. And it's quite fun to do some of these computations. If you ever get bored. Okay, so I threw a lot of definitions at you, but I think really the best way to show you what a scattering diagram is by example. So let's go back to our running example. And so here, our seed gave us two basis vectors. So you should think of these as, it would help if I switched to the drawing tool instead of the mouse. So you should think of these as these two basis vectors, right? So the standard basis vectors. And then that means that this vertical wall and the horizontal wall are the initial walls of our scattering diagram. And the fifth wall was filled in by some mysterious process that I absolutely refuse to explain. But it is the correct wall and it goes there. And this diagram is living on some lattice M-circ that could be complicated, but because this is the simplest example, it turns out to just be sort of the lattice where every integer point is in the lattice. So we lucked out and we don't have to worry about the lattice being complicated. And then there's one chamber of the diagram that's special. So it's the one I highlighted here. We call it the positive chamber. And the reason it's special is because, so one, if you take the inner product of any point in that chamber with one of the basis vectors, you get a positive, something positive, right? And then also later on, we are going to want to do things like actually use this diagram to compute some stuff about cluster algebras. Like it might be nice to be able to find out how to write cluster variables in terms of our initial cluster. That's a thing that cluster algebraists get really excited about. And it's going to turn out that this chamber plays a special role in those computations. Okay, so I want to translate a little bit into the language of cluster algebras. I said some of these things already, but I'll say them again in a little bit more of a precise way. I think probably Esther and Libby will find this interesting, and other people might find it a little confusing because they're trying to synthesize two sets of new definitions. So that's okay, you can just ignore this slide. So the exchange matrix that we're used to in the cluster algebra setting is encoding the skew symmetric form and the choice of integers for this scattering diagram. So those two things, I guess you could also alternately think of them as encoding the exchange matrix information. Here, the cluster variables, as I mentioned, they're showing up by taking the z variable and raising it to one of the basis vectors. So for example, here z10 is going to be x1 and z01 is going to be x2. And these are the A variety. And then I'm not going to draw anything related to it whatsoever, but the coefficients would show up as z raised to these particular scalings of the dual basis vectors, and this would encode stuff about the X variety. And then I don't think I called it out, but we do have also a notion of having some index set and then a sub-index set that lets us differentiate between frozen and unfrozen variables. And then the classic mutation relations, these were the ones that I pointed out this binomial structure in, can actually be derived from the mutation of the basis vectors and this matrix that is encoding the skew symmetric form via simple algebra. And I haven't told you how these basis vectors mutate yet, so you shouldn't be able to see why this is true, but it is just sort of an algebraic exercise if you sit down.
There's a question from Galen.
Oh, yeah.
Would you like to ask it?
Yes, yes.
Oh, yeah, sorry, I have something covering the chat, so I'm sorry that I didn't see it.
No problem. No, I put in there like 5 seconds ago. I was just asking, you said that the EI, FI, and EIJ can be recovered via simple algebra. And I was curious if like you could write down a single formula for an arbitrary scattering diagram that tells you like what the relationship.
Oh, I see. So I think, let me see if I can find the slide that I want to point out. Okay, so these are the mutation relations for the EI, FI, and epsilon ij. So the way that you do this is you just sit down with the fact that, again, if I switch to the drawing tool, this would be better. So you remember that you have these relationships. And if you take these exchange relations and you plug them in up here, so for example, if you want to find xi prime, you start with z to the ei prime, plug in this expression for ei prime, and you can just do algebra and you'll see that you get the original exchange relation. So there's no real insight to get there other than that they are literally the same thing, like they're encoding the same dynamics. Gotcha. Yeah, thank you. It's a good question. I definitely sat down and did this exercise and it was illuminating for me, but I think maybe not illuminating to see in the context of this talk, which is why I did not inflict the algebra on you. Okay.
I also want to mention just that I'll keep an eye on the chat, so don't feel like you need to be watching it.
Okay, great, thank you. Yeah, I wish my screen was bigger, but I have 13 inches of real estate, so.
It's sometimes confusing when like people are having like side conversations that get answered in the chat, or someone says like, oh, that was cool. So I feel like it's better to have someone else looking.
Yeah, it can steal attention a little bit. I noticed that when I'm teaching.
Like Galen said earlier, like the lattice is complicated as kind of a comment. Like, so I'll let you know.
Yeah, the lattices are kind of subtle to think about because I'm going to completely sweep this point under the rug, but when you do some of the, I'm going to show you these computations called like wall crossing and path ordered products. When you do these, there's an inner product involved and there's actually like some scaling inside the inner product based on the scaling of the lattice that you're on. And so I managed to confuse myself for several weeks doing these computations wrong continuously because I would forget that like sometimes when you get 2, that actually means 1 because you're in this scaled lattice. So there's lots of opportunity to confuse yourself if you're as easily confused as I am. So eventually then I just wrote software to do this for me so that I could stop being confused. Okay, so if we go back to our example, I'm going to point out a couple observations. Again, I think these will probably be mostly interesting to people who have a little familiarity with cluster algebras. But so one statistic that we like in cluster algebras is something called a G vector, which appears as a exponent, sort of. But basically, there's a unique G vector for each cluster variable depending on the initial seed you picked. And so these are sort of an interesting set of parameters for us to look at sometimes. But so each G vector of the cluster algebra is actually showing up as the support of a wall. So if you are familiar with type A2, you'll know that the G vectors are the ones that I list on this slide, and you can look and verify for yourself that they are indeed showing up as the support of each of these walls. And then each chamber here, you could think of as corresponding to a different cluster seed. So when we think about choosing a seed, we have to choose a cluster or a set of cluster variables to be our initial cluster variables. So here, one choice was for us to choose the variables. Oh, again, I'm so bad at switching to the drawing tool. So one choice, the choice we've been making, is to look at the variables that I've been calling x1 and x2. It turns out each of these other chambers corresponds to a valid choice of two cluster variables that I could have started with instead. And so one nice sort of structural property this is hinting at to you maybe is that in some sense, crossing one of these walls is kind of like mutating. And in fact, when I say kind of like, I mean literally is. And I'll say a little bit more about that. But so that should also be a little inspiring to you when you look at these automorphisms on the walls. Those are coming from these exchange relations. They're doing some sort of mutation. Okay, and then the other thing that I'll say is that I mentioned that from a geometric standpoint, we study these by studying varieties. And so the way you build the A variety from a diagram like this is you associate an algebraic torus to each chamber. So there, the variables in that for that torus are the possible initial cluster variables. And then you glue those tori along the maps given by wall crossing, which I'm about to define. And so in some sense, that's gluing these together based on the mutation rules. So you're encoding both your choices of initial variables and the structure that you get from mutation. Okay. So wall crossing is basically telling you, how do I hop across one of these walls? So here what we're going to think is that we always start with some monomial, and a monomial starts at the lattice point that its exponent is, right? So if I start with the monomial z11, I'm starting at lattice point 1, 1. And then I'm traveling along paths in the diagram. So the picture that I can draw for you is, let's say I start with the monomial z0, -1. Then I'm starting at this point down here on the bottom half of the vertical wall. And I could travel along this path that I've drawn. And this path sort of suggestively crosses exactly one wall. And there's a definition for how crossing a wall acts on that monomial. So I take the wall crossing automorphism on the wall, I raise it to some inner product, and then I multiply it by the monomial. And maybe the one thing I'll say is this n naught that appears in that inner product is a normal vector to the wall that you're crossing. And there's some choice here. You can choose either the normal vector that opposes the direction of travel or the one in the direction of travel. It doesn't so much matter as long as you're making a consistent choice if you're crossing multiple walls. Usually it's easier to pick the one opposite the direction of travel, just because then we get nice positive numbers, and we love positive numbers. So here's an example computation. Don't feel like you need to track all of the details, but so basically we took our monomial and we multiplied it by the function on the wall, and it turned out that the inner product just came out to be 1, which is an artifact mostly of the fact that we're in this very simple example where we don't have complicated scaling of the lattice, and we don't have integers other than 1 appearing in our matrices. So we don't have to just constrain ourselves to crossing one wall at a time. We can cross multiple walls in something called a path ordered product. And so that just means, you know, in order, we apply these wall crossing automorphisms. So if we extend that path that we were following before, then that means, so first we cross this, okay, one of my labels here is wrong. So this first label should be crossing the wall labeled 3, and the second one should be crossing the wall labeled 1. So just ignore these tags that I tried to put in to be helpful, but forgot to modify from wherever I was modifying this example from. So I was anti-helpful. But so basically you just you do this process twice, and because you're now applying the wall crossing automorphism to a polynomial, you do this by just applying it independently to each monomial that appears. And so you might ask, you know, why are we playing this game? Well, the reason we're playing this game is because each this gives us information we care about in cluster algebras. So one thing we often care about in the cluster algebra world is something called a cluster monomial, which is just a monomial in terms of the cluster variables. So any product of the cluster variables. And so it turns out that each lattice point corresponds to a cluster monomial, and that you can express that cluster monomial in terms of the initial cluster by taking a path from that point to the positive chamber. And I said earlier that the G vectors of the cluster variables appear as lattice points. And so you can compute expressions for the cluster variables in terms of the initial cluster by taking paths from that point to the positive chamber. And this is something we often want to do. These are the sort of Laurent polynomials that are very celebrated and interesting to us. Okay. And so now I can tell you a little bit about the, I guess, secret sauce that goes into adding these extra walls onto the initial diagram. So there's this notion of consistency. And a diagram is considered consistent if anytime I walk in a closed loop, I get a path-ordered product of 1. And it's not always obvious this will happen. Sometimes your path-ordered products get really, I think the technical term is gnarly, and then they start simplifying and you'll end up with 1 if you drew the right diagram. If you want to entertain yourself, you can guess what a diagram is, keep doing the path-ordered products, and then modify your wall crossing automorphisms based on what seems to be going wrong. If you're me, you can spend a couple months doing this. And it's entertaining and good for your character, just like eating broccoli. But so the way that one way that you can build the diagram from the initial scattering diagram is to check if a closed loop gives you a path-ordered product of 1, and if it doesn't, often it will suggest what wall you should put in. This is kind of slow and laborious in any example larger than A2. So there are actually better algorithms that you can use, but I'm not going to talk about them at all. So here, right, our initial diagram consisted of the vertical and horizontal walls, and we could have used consistency to add that 5th wall. Okay, so the theta basis, which is one of these good bases, can be defined in terms of path-ordered products. And so the way it's defined is it's just we take any lattice point, you take a path to the positive chamber, and that gives you a theta function parameterized by that point. And the whole collection put together gives you what's called the theta basis. And so these path-ordered products are not bad to compute in areas where the walls aren't dense. Like it might get a little gnarly. You might want a computer to do it for you. But the problem is that when you get outside of these really simple examples, most of the time there are areas where the walls are dense. So for example, if your exchange matrix, so the exchange matrices typically have the form 0b minus c 0. So when this product of b and c gets large enough, and by large enough, I mean not even really that large, right? So as soon as it gets to 5 or above, then you end up with this region where every wall of rational slope appears. And we call this region the Badlands because it's bad if you want to calculate these path-ordered products. So although this is a perfectly good definition of the theta basis, it's not always a very practical definition. So this motivates the idea of a broken line, which is going to use this scattering property that Galen anticipated. So roughly speaking, I'm not going to give you the precise definition because it's a little laborious to parse, like every definition in this talk pretty much. So roughly speaking, a broken line is a collection of piecewise linear paths. They start with a particular slope. When they hit a wall, they scatter in particular ways. And we want to collect all the ones that end at a certain point that we care about. So for example, if we wanted to do this for the initial slope 0 minus 1, and a point in the positive chamber, we could fiddle around on paper for a while and we would come up with this diagram. So there are 3 piecewise linear paths that take us to this point. And then if we sum up the terms on the last region of linearity for each of the paths, we actually get the theta function, or in this case, we get the cluster variable. So this is how the theta basis is defined in terms of broken lines. So here, this definition just says what I just said verbally. And then in this definition, you can see that I summed over these last three monomials. And if you have any familiarity with how cluster algebras of type A2 look, you can convert this back into the, in terms of x1 and x2, and you can look at it and nod to yourself and say, yes, indeed, that's a cluster variable. Okay, and then we talked a little bit about this earlier, so I won't say too much about it, but there are relations we could use to define seed mutation for the scattering diagrams. And then honest to God mutation between the different chambers or between different clusters is defined in terms of a certain pullback of a certain birational map. Please don't try to track these details. This is kind of complicated. And if you tropicalize this pullback, then you get a map that lets you do mutation on the scattering diagrams, basically. So the essence of what's going on here is it would be a kind of annoying and fiddly if every time I wanted to do mutation, I had to go back to the data, mutate it, and then draw the diagram again. What I would like is I would like some map that lets me say, if I've already drawn a diagram for one seed, here's how I draw a diagram for a seed that I can reach by mutation from that seed, right? I don't want to have to do this stepping back and forth process. I want to just stay in the world of diagrams. And so there's this map defined in this sort of complicated way that I explained. And the way we use it is we apply it to each of the walls. And then there's one wall that's sort of special that we do a special thing to. But so the picture, just look at the picture here, because I just want to give you a flavor of how these diagrams change. I'm not going to say anything other than this example. So here I tried to use color to sort of suggestively highlight things. So here you can see that the left side of the diagram is fixed. It doesn't do anything. And then on the right side, we have some sort of shearing. So this TK map is a piecewise linear map. It always fixes half of the diagram and it shears the other half of the diagram. And the half of the diagram that gets fixed is the half that that is basically like if I took the, so if I look at the basis vector for the direction I'm mutating in, the half of the diagram where the inner product with that basis vector would be negative gets fixed, and the half where it would be positive gets sheared. And so you can amuse yourself by doing lots of diagram mutation. If you're me, this will keep you very happily occupied for a summer. And you can draw lots of pretty pictures like this. And you can encounter all sorts of fun quirks, like this map, this TK map is not an involution. So then there's a notion of like equivalence of diagrams because, you know, like mutation itself is an involution. So really we don't want this to not be an involution, right? So then you say, oh, well, it's an involution up to equivalence. And you can, again, occupy yourself happily for a while, like testing that various diagrams are equivalent and figuring out, you know, can I visually tell and all sorts of fun things. Okay, so switching gears, I don't have a lot of time left. So what I'm going to do is I'm going to basically tell you what the generalized object is, and then I'm going to really fast flip to an example and show you how some of this changes. So I'm going to try to cram this all into about, I think I have about 5 minutes, right?
Yeah, it's not super strict at exactly the moment we end, but people might have stuff at the start of the hour, so.
Absolutely, yeah. And I think also there's a limit to how much math you can absorb at a time. So I'll try to give you the highlights of what we did to this narrative.
Sounds good.
So there are a lot of generalizations of cluster algebras. And the one I want to talk about is one that I think is a very natural generalization. And so in this generalization, introduced by Chekhov and Shapiro, instead of requiring this binomial structure in our exchange relations, we let those exchange relations have arbitrary numbers of terms. So instead of that binomial that I highlighted way back when for Alex, I could have had a polynomial of an arbitrary degree. And basically I do this by, I add a little bit of information. So basically for each cluster variable, I could just write down a polynomial that's going to give you the number of terms in its exchange relations and the degrees of each of those terms and the coefficients of each of those terms. And so then I can modify all of my mutation definitions. And so here you should just look at the blue highlighted bits. Those are where these are different. So you can see that basically we add some longer polynomials in places and we get some extra exponents. So the upshot of this is that when I go back to what should be a very simple example, so this was the example we've been playing with, but I increased the degree of just one of the exchange polynomials by just one. And already just doing one mutation, I start getting more complicated things. I start getting terms that have squares in them, and I get 3 terms instead of 2. And if I go through and explore the entire cluster algebra, I get these much more complicated looking cluster variables, right? And this isn't even all that bad. It's just the very simplest thing that I could have done. So these get really gnarly really fast. That's the technical explanation. So in our work, we focused on a subset where when I write out one of these exchange polynomials, I'm going to require that they be what I call reciprocal, which basically means that if I reversed the order of terms, so I swapped like the lowest degree term with the highest degree term and so on, that the coefficients are fixed under that operation. So you could also call this maybe mirrored or something like that. That might give you a better mental picture. And so then we went through and we sort of updated this construction so that it would work for these algebras. So to do this, you have to add some information to the fixed data. So you have to add information about what the degrees of these exchange polynomials now are. You have to add some information about the coefficients from the exchange relations. And then you also have to, change the definition of the initial scattering diagram to reflect the fact that the functions we're attaching to our walls now often have more terms. And so one point that I'll make is that you might be saying, hey, wait, if you're thinking about these reciprocal ones where they're fixed under this operation, like, why are we not putting this coefficient information in what you're calling fixed data? And the answer is that I'm leaving this construction open a little bit because I think that I should be able to make it work for non-reciprocal algebras also with a little bit more time and thought. So I'm purposely defining this in a way where it won't have to be redefined so that these might not be reciprocal later. And so as before, we have notions of path-ordered products. Here I put an example doing the mutation that I would have shown earlier. But the upshot of this slide is just that path-ordered products, you define them the same way, it all goes through the same way. And then you get some changes in the mutation relations at the diagram level also, which you would hope you would, because I've been telling you that these are the same exchange relations. And it actually looks sort of beautiful and simple here, right? Because you just add some RKs in a few places. So once you make the right educated guess, you could sort of fill this in. And then you also have to modify this map whose pullback is defining the mutation map for our diagrams. And it's all just algebra and bookkeeping, basically. It all kind of goes through once you make the right decision about how to modify the map. And so you can mutate these diagrams also, and you can get these sort of wild and fun looking things. And just like in the ordinary case, we have a notion of broken lines. And so the only thing that's different here is that because we have more terms in our wall crossing automorphisms, there are more ways for things to scatter. So starting with the same initial slope, you start getting more terms. And this makes sense to us because our cluster variables have more terms, right? And if we can find cluster variables and theta functions using broken lines, then by God, the broken lines should have more terms. And so the theta basis, if we define it in the same way, it turns out that you can go through and prove many of the same properties as for the theta basis in the ordinary cluster algebra case. So in our work, what we did is we sort of went through and did this, right? We made these definitions, and then we went through and checked that you could still make things go through. And there are places in the proofs that rely on the coefficients being reciprocal. So there are places where like the algebra won't work if the coefficients aren't reciprocal. And I have some thoughts about how to get around this, but I want to point it out because I do want to say that like there is in some sense like a reason that we might have to make this restriction. You have to do a little bit of work to try to think about how to get around it. And so one of our main results is that that these theta functions are a legitimate basis. And then I was going to make an aside about something called companion algebras, but I think that I will not make this aside. So I think the moral that I want you to take away is that we can tell this story for this generalization, and that gives us a way to define the theta basis for a subclass of these generalized algebras. And then there are some sort of natural ways that I would like to continue working with this construction. So one thing that I said that we care a lot about is positivity. And right now, we don't have, from this work, we don't get positivity for these reciprocal cluster algebras. So in one of the algorithms that I glossed over for coming up with the scattering diagrams, there are arguments you can make using that algorithm that lead to positivity. And that algorithm gets a lot more complex with these generalized cluster algebras. So I've tried to work out some examples because I think that you should still be able to use that algorithm to argue for positivity. But even in very simple cases, so the way the algorithm works, basically you take like you make some deformations of these diagrams. So you pull some walls apart into multiple walls that are parallel, and then you look at intersections in certain ways, and this adds walls depending on certain conditions. And in the ordinary case, the amount of walls that get added are kind of manageable and not too bad. But I tried to do this for the sort of simplest generalized example I could think of. And really fast, I had like 200 something walls. And it just got really, really sort of unmanageable to do by hand. And so I think that a little bit of programming could help with some examples, but also the sort of ultimate argument you want to make here is that certain exponents will be positive. And I think that with a little bit of clever algebra, I might be able to make this argument without necessarily needing to walk through the entire algorithm. So I think there are some promising directions to get positivity here. And that would be exciting for several reasons. So one, so right now, positivity is known for, I think, all reciprocal generalized cluster algebras, but the other direction to take this, like I've been alluding to, is that I think this construction should be extensible to non-reciprocal generalized cluster algebras. And in that case, these two things together would give positivity for a new class of generalized cluster algebras, which would be quite interesting, I think, because it's widely believed to hold. But as far as I have asked and read, there's no proof written anywhere in the literature. It's just sort of believed. And then I also have some thoughts about a tactic. So another thought is there's another conjecture by Chekhov and Shapiro that says these generalized cluster algebras should appear as subalgebras of ordinary cluster algebras. And so then there might be something interesting to say about like quotients of scattering diagrams. And so you might be able to make an argument from that direction also. So I think that this is sort of a pretty fruitful area with a lot of things left to explore. And I'm pretty jazzed about getting to continue exploring them. So I think that that is all that I want to say. Let me show you some references. I know that that was a lot of information to take in, but I'm happy to answer any questions or to direct people to things to read if you want something a little bit more sedate.
Okay, let's thank Elizabeth.
Alex, You want to thank Elizabeth?
Sorry, we did it at the same time, but yes, let us.
So, I see that Esther has a question in the chat. Esther, would you like to unmute yourself and ask?
Oh, sure. Wait, Elizabeth, did you say someone's already proved positivity for the reciprocal case in general?
So let me think. I know Chekhov and Shapiro.
I thought it was a conjecture.
I'm trying to, so they can definitely conjecture it for all of them. I think you're right. So yeah, actually, I think you're right. I think maybe they don't have positivity for all reciprocal generalized cluster algebras. It might have just been the ones from orbifolds.
Okay, yeah, okay. So yeah, that means there's more you can prove then.
Yeah, I need to go back and look at their paper because they also have something about like all rank 2 generalized cluster algebras.
Oh,
maybe.
yeah.
So there were like a couple subclasses I think that they said they had positivity for.
Okay.
And I should know exactly how they intersect, but off the top of my head, I don't remember if that ended up meaning it was for all reciprocal cluster algebras or like just those of a certain rank and below.
Oh, okay, gotcha. Cool.
I actually have a question. Maybe I should wait for a minute to see if other people have questions as the host.
I have a question. So I guess I want to hear a little bit more if you had more to say about like where the generalized cluster algebras like come from or why they're defined like in the first place.
Yeah, so I guess that feels kind of like two questions in one, right? So like you're kind of asking about the definition, but also maybe like where these show up and why we care about them. So let me answer the second question first. So I think, Libby, I think you're pretty comfortable with like the surface model for certain ordinary cluster algebras, right? So some generalized cluster algebras can be modeled as triangulations of what are called orbifolds, which are basically surfaces with a new type of singular point that you add. So you don't just have marked points and punctures, but you also have orbifold points. So in some sense, like that nice combinatorial model might be motivating. Also, these generalized cluster algebra structures show up in places in physics, and they come up in like certain areas of, I think, higher type Mueller theory and some of the places where you see cluster algebra structures. So I think in the same way that cluster algebras became really interesting to people because they showed up in all these places, this generalized cluster algebra structure also shows up in a lot of places. And then another way that I could answer that question is, so one of the really sort of celebrated features, or maybe I shouldn't say celebrated, but hallmark features of ordinary cluster algebras are those binomial exchange relations, right? So when you're thinking, if you're just sitting in a room and someone says, Libby, come up with a generalization for cluster algebras, one sort of natural thing you might do is you might say, well, okay, well, what if I had a trinomial instead? Or what if I had 4 terms instead? And this is that generalization. So in some sense, it's just like a natural thing that you might wonder, like, does this still have all the structural properties that I like about cluster algebras? And it looks like the answer is yes. So I don't know if that answered your question. Hopefully it helped.
Yeah, thank you.
Other questions? Okay, so I'll ask my question, which I should warn you is completely uninformed. But so I see Nathan Reading's name on the very bottom of that reference list, and it makes me ask if there's a connection between these scattering diagram models and reflection groups. Like, is there a Coxeter story here?
Yeah, so I think that the answer is yes, but I am actually uninformed here. So I know that, so Nathan Reading has this really nice paper called A Combinatorial Approach to Scattering Diagrams, and he does talk about the connection to Coxeter groups there. And a long time ago, I gave a presentation in a class that Greg taught based on that paper. And so the root systems, those can show up in these diagrams as like the basis vectors, I think. I think that's the story, but it's been long enough since I thought about it that way that I don't want to say that super confidently and mislead you.
Okay.
But so also, like, if you ever look at Nathan Reading's work on this, which you may or may not, like, you might not have a reason to look at it. He draws his diagrams in a different way based on he has like a particular way that he likes to draw these root systems, and that informs the way he draws the diagrams. So I do think that there's a connection that's like kind of intimate. And the other reason that these things get connected is because like the Dinkin diagrams are used to classify certain types of cluster algebras, right? So there's sort of this intimate connection there.
Right. Part of me was hoping also that there's some way to cook up a cluster algebra where crossing the hyperplanes replaces, so if I cross like hyperplane HI, it would replace XI with 1 minus XI or XI minus 1 somehow. But I don't think that you could cook up something with the exchange relations that you had.
Yeah, so I think you would have to define wall crossing differently.
Okay.
But yeah, no, there might be something interesting there. So if this is something you ever want to play with, we could sit down and be very uninformed and see if it can be coherent.
Okay. Maybe after job applications.
Yeah, so maybe in the spring you and I can play.
Okay, great. You're on.
Yeah, because you know a lot more than I do about like hyperplanes and Coxeter groups and things.
I'm also very much a beginner at all of this Coxeter group stuff. So
that's okay. I basically spent the last year doing every computation wrong and then sending email to Mandy saying, Mandy, I don't understand, nothing works. And she would very nicely write back and be like, well, actually, remember that the inner product has scaling. So that is to say that I live in a very glass house.
Very relatable. Okay, are there other questions now that we've... So if there aren't other questions, maybe we'll thank the speaker again and turn off the recording. So we can thank Elizabeth either with a reaction or by